All right, we're going to continue with the, I'll actually finish up chapter 6 and then move on to chapter 7. So we were talking about the method of successive approximations last time. And what we had was we had a volume. What was the volume? We did a. Did we use 1 bar or did we use 1 atmosphere? I think we used 1 atmosphere, right? Atmosphere. And so we calculated volume, which was equal to nRT over P, and the number of moles was, what was that again? 10.3. Somebody have that? The numbers from last time? Okay, 10.3048 mole. 10.3048 R mole. R is 0.08206. Let's just double check this calculation. It came out pretty much. Liters, atmosphere, mole, Kelvin. T was 290 Kelvin. P was 1 atmosphere, correct? And so how much, what was the volume on this? Two 377, was it? Okay, 255.3 liters. That's with the ideal gas law. And then we are using the real gas law. Do you guys have this one in your notes? It came out A times M squared over V squared. V minus MV is equal to nRT. So N times R times T. Well, it turns out that A and B in the table, we need units of bar. And so we have to convert it to bar. So this was 10.3048 times R. This will be moles times R, which is 0.08206 liters atmosphere per mole Kelvin times. Now we go from atmospheres to bars. So it's 1.01325 bar per atmosphere. Times 298 Kelvin. And, on the right side, can somebody just double check this calculation on the right and tell me what they get? somebody have it? 25 point. On this side, we get 255.33. Okay, 255.33. So last time there was a mistake in the calculation. I asked somebody to calculate, and then there's some kind of error in this. And so what we do in the method of successive approximations is we leave the right side as is. And then on the left side, we try to fix it. Now the units are, I don't care what the units on the left side are necessarily. But the units here are going to be liters times bar. Liters times bar. That's what the units are. So on the right side, it'll be liters times bars too, because volumes in liters, pressures in bar. Well, basically, all we want to do is we just want to make them match. And so the pressure here, we have to use the bar pressure, which is 1.01325 bar. And then A, we looked that up off the table. The A value is 9.39. Actually, to make our life easier in successive approximations, I know the units are going to work out. And so I'm going to leave them off because the units are going to cancel. We get liters bar, liters bar, liters bar cancels liters bar. It should be okay. And so the left side equals the right side. And so A was 9.39. N is 10.3048 moles squared. V, the volume, is what we're solving for, V squared, minus V minus NB. N, again, is 10.3048, and then 0.905 is B. And so let me write it down here. This is going to be times V minus N D, 10.3048 minus B, which is, or times B, excuse me, which is 0.09. Or 5. And so when we do this, we want to simplify this. So this is as much as possible, that is. And so we're going to get on the left side of this is this. Left is going to go 1.01325 plus, what's 9.39 times 10.3048 squared? What do you guys get? I got 965.257. The more digits we have, the more we're going to be punching into the calculator. And so sometimes we'll try to limit it, not carry so many digits. Otherwise, calculations can take a long time. B minus, okay, what's 10.3048 times 0.905? We have 9.168. Okay, so this is left side. We want that to equal the right side, which is 255.33. And so here, now this is correct. The previous one was incorrect, so just eliminate it. That's why it wasn't working out. And so we're going to use the initial guess, which was 255. We'll just go 255 since this is a guess, so we can save some work. And so the right side is going to be 255.33. Okay, so when you plug that into your calculator, you plug in a volume at 255, the left side comes out to 261. And so with this, then we get the left side at 261, the right side is 255, which is, this is just coincidental. This 255 and this 255 aren't the same thing. Right, this is the volume. And so it's 261. Well, 261 is too big, right? The left side's too big, so how do we want to make it smaller? We'll just change the V. So what do you want to guess as your next V? Normally, if we want to make it smaller, we'll make V smaller, right? Should we make V smaller? The problem is this is V squared in the denominator, not in the numerator. And so really we should make V bigger. Right? Should we make V bigger? Well, let's try it. So the next guess, what do you want to guess? Let's just make it a big change to see what happens, 265. And so we go up to 265, and then we plug 265 in here and here, and then see what the answer is. Since I don't want to wait for calculations, so I don't have much time, I'm just going to use Excel to calculate it for us. And then the left side comes out at 251. Now it's too small. We went too far, right? And so what do you want to guess next? Oops, no, I'm sorry, this is 265. 265, it comes out to 271. Oops, we went the wrong way. So I was wrong then, because going bigger made this one bigger. So we need to go smaller, right? And so let's go 245. And so if I go 245, well, this is the nice thing about Excel. Excel does repetitive calculations quite nicely for us. And actually, you can program Excel to converge on some number if you give it some criteria for convergence, which we're going to talk about the criteria for convergence. We get 251. 251 is too small, right? And so tell me what your next guess is. Think. What should you guess next for B?
I use 258, 255, and 7.
You use 258? Wow, that's good. How many guesses did it take you?
5.
Oh, well, sometimes that happens. Sometimes people, when I'm given this problem, successive approximations, some people fill up 2 pages worth of guesses, and some people just have a few, they just nailed it. But you don't have to worry. If you're going 2 pages, 3 pages, ultimately you should get it, hopefully. It depends on if there are multiple wells, but since we have a very good target, that should be it. And so if we guess 258, that would have been a reasonable guess. Let's do that. Guess 258. Oh.
He's giving different numbers.
Yeah, I get 264 at 258. 264. Let me see, maybe my equation's not set up correctly. Take a look at my equation here. If I look at the equation, this is the equation here. So 1.01325, 9.39 times 10.3048 squared divided by v squared. So 10 squared is about 100, so it's 900 over 900, so that should be about right. 10 times 0.09 would be 10 times 0.1, so about 1. Oops, is that right? Maybe this is the error here. What's 10 times 0.0905? It's 10 times 0.0, it should be 0.9. I screwed it up, right? 0.0905 should be about 0.9, not 916. Sorry. 0.91668. 0.9168. So unfortunately, you'll have to do some more guesses. That was very good, though, as far as the number of guesses. Yeah. Well, anyway, 258. It turns out 255 is 261, so that's still too high, right? And so it's between 255 and 245. Do you see that? 255 is 261, 245 is 251. And so what's halfway between that? Let's try what next?
Try 249.
Okay, well, I would say 250, but let's try 249, that's fine. Oops, wow, good. 249. At 249, then what we get is we get the left side equal to 255.34. 255.34. All right, is that good enough? 249 liters? Well, it depends on what kind of precision we want in this particular problem. Okay, so there's two ways you can know that you can stop guessing. One way is, you know, this is not very precise, is it? There's only 3 sig figs here and no decimal places. And so we probably want to narrow it down even more, you know? That's one way. Or we look over here, well, this is pretty precise, 255.34, it's supposed to be 255.33, that's pretty good. That's actually really good. And we have to take a look at the original problem to figure out, you know, what we should do. And so let's go back and take a look at the original problem. Actually, the original problem was 1 pound of, this is not a book problem, I forgot. It was 1 pound of propane, right? And so if we say exactly 1 pound of propane, then we'll get 255.3 liters. Well, let's take another guess. Maybe we'll just go with 1 decimal place at least. And so, well, 249 is at 255.34. Let's go to 249.9. Let's see what that brings us. 249.9 brings us to 256.2. I'm going the wrong way. Actually, no, I'm at 248. Sorry, 248.9. If we go to 248.9, we went too low because it's 255.24 rather than 255.34. So we want 255.33, and so that makes me think it should be 248. So it's between 248.9 and 249.0. So let's go with 248.99. And so that gave us 255.33, which is our target. And so we just do some guesses here. And so what we did was we did 248.9. That gave us, on the left, 255.24. And then we went to 248.99, which brought us to 255.33. And so that looks good. And so the volume is 248.99 liters. This is using the van der Waals equation versus the ideal gas law. The ideal gas law told us the volume is going to be 255 point, what was it, 7? What was the ideal gas law? 250. 0.3? Okay, well, coincidentally. I just picked, I picked, I shouldn't have picked 1 pound. I should have picked a different mass so that these numbers were significantly different, but it's okay. And so ideal's 255.3, this is 248, which tells me, you know, the what? Intermolecular forces or the volume of the molecules are coming into play here. The volume is less than what we expect. So are the intermolecular forces or the volume of the particles coming into play? Well, anyway, which one's more accurate? Would you say, which one would you have more confidence in? The ideal gas volume or the van der Waals volume? You would have more confidence in the van der Waals volume because it takes care of the things. And so let's calculate the percent error, assuming that the van der Waals is correct. And it should be much more accurate. And the percent error is the, what we call, we'll just do the ideal minus the van der Waals divided by the van der Waals. So this is experimental minus theoretical. We'll take the van der Waals as a theoretical times 100%. And so what kind of error, percent error, did we have when we calculated this using the ideal gas law? You know, it's a lot easier, wasn't it? We didn't have to do the successive approximation stuff or anything like that. And so let's go ahead and see what it is. It's going to be 255.3 minus, actually we should go, the ideal gas law, we should go maybe 1 extra 3, whatever it was, 248.99 divided by 248.99 times 100%. And so what kind of percent error did we get? Particular problem. What is it? 2.5%? Is 2.5% error a big deal? No, it depends. You know, depends. If you're just using propane for the barbecue out in the back, is that a big deal? No, so just use the ideal gas law. You know. It'll give you a little bit of error, but save you a lot of work, right? If you're doing this because you know somebody's going to purchase, you're going to purchase some propane, right? Or somebody is going to buy some propane. Somebody wants to buy some propane, and they want to buy 1 pound of propane. They're going to buy it from you. Are you going to give them 255.3 liters, or are you going to give them 248.99 liters? This is your propane. What do you do? You would give them 248.99, that's a pound, because if you give them 255.3, you're giving them 2.5% more than a pound. You know? In other words, what does that be? 1.025 pounds of propane, right? Okay, so that's it. So, you know, that was one of the least ideal on our chart. In fact, that was the least ideal on our chart, wasn't it? And still, under normal conditions, we only got a 2.5. Now, what if the temperature were very low? If the temperature were very low, would the discrepancy be greater? In other words, would the error be bigger or smaller between these two values? Temperature were very low. Temperature were very low, the gas behaves less ideal. The gas behaves less ideal, that means the ideal is going to be worse. It's going to be a bigger error. And so the error is going to be bigger. The percent error is bigger. If the temperature is very high, then gases behave more ideally. What about pressures? If the pressure is very high, would there be a big difference? Yeah. At low pressures, 1 atmosphere is considered low pressure, right? What's considered high pressure? 100 atmospheres, yeah, 10 atmospheres, etc. All right, that's it for chapter 6. You can take a look. There's some other applications in there. You know, applications, since I don't have that much time, we'll just verbally talk about it. You know, like Graham's law. Have you ever heard of Graham's law? Graham's law is involved in diffusion and effusion processes. And so we can take a quick look at that here. This is what I was trying to show in lab, but it was unsuccessful because I think the concentrations are kind of low. But if you put hydrochloric and ammonia, this is ammonium hydroxide. All the old bottles are labeled this. Ammonia AQ escapes from ammonia AQ, but labeled ammonium hydroxide in this photograph. Somebody must have complained because, you know, is a bottle of this mostly ammonium hydroxide or is a bottle of this mostly ammonia? Mostly ammonia. You know, ammonia is a weak base. Weak bases do what? Partially hydrolyzed in solutions. So, well, this is what I was trying to show. Do you see that smoke? You know what this smoke is? This smoke is ammonium chloride. And ammonium chloride, just small crystals of it creates this smoke, and eventually it'll settle on stuff and coat it with a white powder. But anyway, you can see the difference in speeds. Which one moves faster, HCl or ammonia? Can you tell which one moves faster by where they react in space? Immediately when the HCl escapes, it's attacked by ammonia. That means ammonia is moving much faster than the HCl. If they're moving at the same speed, they meet in the middle. And so this just shows that ammonia moves a lot, well, it's going to move a lot faster because at room temperature, they both have the same kinetic energy, average kinetic energy, but ammonia is much, much lighter than HCl. HCl is a lot heavier, so the average or the RMS speed is much slower. Well, anyway, going back, this is called diffusion. You know, even though something moves at 1,000 or 500, like for example, spearmint. The spearmint, you know, the molecule that gives spearmint its taste and its smell is very heavy, and it moves, let's say, at 500 miles an hour rather than 1,000 miles an hour at room temperature. But at 500 miles an hour, a spearmint molecule should be able to get to San Francisco in an hour, right? But will it ever make it to San Francisco? Probably not. You know, even though it's moving 500 miles an hour, what is the collision frequency of that? Extremely high, right? It's just colliding back and forth. So it'll travel long distances. So if you're brewing, let's say you're brewing spearmint tea in the kitchen, how long will it take to travel to another room? It takes a long time, right? For the smell in the kitchen, well, a relatively long time considering things are moving so fast, right? To go from the kitchen to wherever else. And the reason is because diffusion has, a molecule has to travel a great distance to get from point A to point B because there's so many collisions. And so it's going in so many directions. And so eventually it makes it there. And effusion is escaping out of a hole. So when we think about this, we have Graham's law of diffusion or diffusion. You know, this can be used for both. Effusion is a gas molecule traveling through another gas. Effusion is a gas molecule escaping out of a hole. So this shows some diffusion. So the blue gas is going to diffuse, the white gas is going to diffuse to the right. It's going to take time. This is just the ratio showing, you know, how much. So how much faster is ammonia? How much faster is ammonia if we take a ratio like this? And we can see how much faster ammonia is. because based on the molar mass. And so the Graham's law of diffusion says the rate of diffusion of A over the rate of diffusion of B is just equal to the square root of their molar masses, flipped. And so, for example, A is inversely proportional to the root of its molar mass, B is inversely proportional to the root of its molar mass. And so if you put ammonia up here, ammonia weighs a lot less, that goes down here, HCl down here, HCl weighs a lot more, and then we can get a ratio just based on the molar masses. And so you can do some calculations. This is just showing rates of effusion, gases escaping. So something like helium, since it's so light, moving so fast, will escape out of this pinhole much faster than a heavier molecule. They're showing hydrogen versus, looks like oxygen or nitrogen. This is probably nitrogen. Hydrogen versus hydrogen is going to diffuse much faster. Well, how much faster? Well, it's going to be the square root of the inverses of their molar masses. That much faster. So you could do some sample calculations there and try those out. We have to move on, unfortunately. Some behind schedule here. We have to move on to chapter 7. Chapter 7 is a tough chapter, actually. It's a tough chapter because what makes it tough? What makes it tough is people don't memorize the jargon or the vocabulary. And they don't memorize the restrictions on the equations, this kind of stuff. And there are lots of restrictions like heat at constant pressure, heat at constant volume. Well, a lot of people don't want to bother with the constant pressure, constant volume stuff, and then use the wrong equation in the wrong place. So we could use the wrong equation in the wrong place, but there's no warning bell that goes off. So if somebody were to use the ideal gas law under conditions at, let's say, 100 atmospheres, would a warning bell go off? Do not use, because you're going to get a really inaccurate answer. Does a warning bell go off? No, the only warning bell that goes off is in your head because you've memorized it, right? Otherwise, anybody could use it. If you gave that to a Chem 4 student and said, okay, let's do a calculation, 100 atmospheres, n is equal to this. What is the volume? They're just going to punch it out thinking they're going to get the right answer because there is no warning bell. Well, thermodynamics is like that. There's no warning bell. You can easily use the wrong equation because you aren't paying or you didn't memorize the restrictions. And most people aren't used to memorizing these kinds of restrictions. This equation is only good under these conditions. It's like that whole gas mixture. How many people really care about Dalton's or Avogadro's mixtures? Most people just say, oh, I know Dalton's, and that's good enough, right? But unfortunately, it's not good enough, and you have to memorize both. Well, thermodynamics has lots of those. This equation is only good under this specific scenario. But it's so easy to use under all scenarios. And so and the good thing is, it doesn't have to be hard if you start memorizing all these things early, The problem is people don't. And so at UCLA, at the bookstore at UCLA, they sell bumper stickers, I passed thermodynamics or I passed P-Chem. It's because so many people fail it because they never bothered memorizing it when they were taking general chem. And so when I took general chem, I didn't memorize any of this stuff either. And so when I was taking thermo, I was on dangerous ground because I didn't know what the heck was going on. Too many symbols, too many restrictions, too confusing. And so then I had to go back and break open the general chem book and start from scratch again, basically. But that's just a warning. So we need to get the terminology down, so that we know what the heck we're talking about here. And the terminology has certain conventions that we need to be very aware of, you know, like negative and positive conventions or this and that, you know. And so let's look at the terminology. There's a lot, but the main things we're going to look at are this. We're going to define the universe in terms of system and surroundings. So the universe is going to consist of two things. The system plus the surroundings. We have different types of systems that we can consider. You know, this is called an open system. This is an open beaker. You know, so let's say we're interested in whatever this solution is. Well, whatever this solution is we can see some steam coming off that, and the steam is going to escape, you know, out into the lab or wherever else. And it looks like a lot of heat is being generated off that. And so we call this an open system because if we're interested in this, we call this the system, and then everything else is the surrounding. And so the system is what we are interested in. You know, it's either the object or reaction of interest. And the surroundings is the rest of the universe. And so here's our object, but part of our object is escaping. You know, what part of the object is escaping? The water here as steam. And so open systems, we don't want the water to escape as steam because the mass of our system will be continually decreasing. We're losing matter. So the definition of an open system is energy is freely exchanged with the surroundings and matter is freely exchanged with the surroundings. What we are interested in are closed and isolated systems. In closed systems, what we have is matter cannot be exchanged with the surroundings. That is, you know, we're going to cap this off so steam can't escape here. And so we have all the water fixed in there in the solution. And so if we start off with 300 grams of solution, that's what we have, 300 grams of solution. That's it. We don't have to worry about how much did we lose as steam. It's a closed system. But closed systems, you know, heat can be exchanged. Not just heat, but there's, you know, there's two ways that, that energy is exchanged in a closed system. And so we're primarily interested in this closed system in which matter is not exchanged with the surroundings. So matter is not exchanged with surroundings. But energy is with surroundings. Now the energy is going to be exchanged in two ways. You know, heat, like for example, if our system's hot, you know, hot just means it has a lot of kinetic energy. You touch a hot object, the atoms or whatever, molecules are moving fast. If it's hot, then some of that kinetic energy can be transferred to the surroundings and warm up the surroundings, right? If it's cold, if our system's cold, then, you know, some of the kinetic energy of our surroundings can be transferred to our system and warm up. And so either our system can cool down or warm up by the transfer of kinetic energy. That's called heat transfer. But there's one other way that our system can exchange energy with the surroundings, and that is called work. So heat and work can be exchanged, and that's energy exchange with the surroundings. What kind of work? Well, we're primarily focused on one type of work, but there's many types of work that can be exchanged, like sound, you know, light. But we're kind of interested in mechanical work, that is volume changes. You know, let's say as the pressure builds up in our system, you know, we could have a container like this with a fixed volume. So as the pressure builds up, you know, well, as long as the container is strong enough, the volume is not going to change. You know, the volume is fixed. So this is what we call constant volume. And so we could have a constant volume system, or we could have what we call a constant volume system. One of the characteristics of a constant volume system is, since the volume doesn't change, then we don't have this kind of expansion or contraction of the system. Expansion of the system, you know, requires work. It's like expansion of a balloon. You know, if you were to blow up a balloon, does that require work or no work at all? Does that require energy to blow up a balloon? Yeah, you're blowing up a balloon, which is the system, and the system volume is increasing, you know, and you're going to do work. Well, how much work are you going to do? Well, that depends. How big a balloon? The bigger the balloon, the more work, right? And it also depends on where you blow it up. What is the external pressure where you blow it up? So if you blow it up at sea level, is one thing, but what if you tried to blow up the balloon like 30 feet underwater? If you tried to blow up the balloon 30 feet underwater, you're going to have to do a lot more work, right? Trying to blow a balloon up. Because the pressure you're fighting against is much higher. And so the system is not always a rigid container like this. The system could be a balloon. If it's a balloon, then it can expand or contract. Or it could be a rigid container like this. A rigid container we call a constant volume system. What would we call a balloon? What do we call a balloon? This is why I spent so much time talking about Avogadro's and Dalton's. Avogadro's is what? Dalton's is what? Dalton's is what we call, this is Dalton's mixture. What do we call that? No idea? Yeah, Dalton's law of partial pressures versus Avogadro's. What's the difference?
Constant volume. It's constant pressure.
Yeah, which one's constant volume, which one's constant pressure? Yeah, Dalton's is constant volume, so the pressures can change. And so fixed volume, constant volume, we would think in terms, yeah, Dalton's, pressure is going to, if we get more gas in there, less gas, the pressure is going to change. Versus constant pressure. Constant pressure, it doesn't have to be a balloon, it could be a container like this. So if we start off with some potassium chlorate and heat it so it decomposes, O2's formed. And as the O2 is formed, the O2 has to go someplace, so it's like blowing up a balloon. All of a sudden, we start off with air in here, and now we got a whole bunch of O2 that's coming in. If this were constant volume, what's going to happen to the pressure? Pressure is going to go up, because as we generate the O2, then Dalton's law of partial pressure says the pressure of the air plus the pressure of the O2 is going to equal the total pressure. That's if the volume's fixed. But if we let the volume expand like this, then we're dealing with what type of mixture? If we let the volume expand, then we're dealing with not a Dalton's, we're dealing with a Avogadro's. And so Avogadro says the volume of the air here plus the volume of the O2, well, the volume of the O2 is going to be this. So the volume of the air plus the volume of O2 here is going to equal the total volume. And so when we're thinking about the systems, when we think about a constant volume system, then we think in terms of Dalton's. When we think about a constant pressure system, we think in terms of Avogadro's, right? And so this would be kind of like the balloon. Well, was there actually work done here? Yeah, this is like blowing up a balloon, The O2 just can't blow up the balloon without having to do some work, and the work is fighting against atmospheric pressure, whatever that is. That's what we call work. And so heat and work are going to be very important. In fact, heat is going to be given the symbol Q, work is going to be given the symbol W. Let's go back here, getting started. An isolated system, sometimes we deal with isolated systems or pseudo-isolated systems. An isolated system is nothing's exchanged. No energy, no matter is exchanged. And so this would be like having a totally insulated container. So let's take a look at energy in a little bit more detail here. All right, but let me summarize this quickly. When we talk about a system, we have to decide a couple of things. What things do we need to decide when we identify a system? Because what's going to happen is nobody's going to tell you what the system is. You're going to have to define the system yourself. And so when we define the system ourselves, what do we want to do? Well, first we want to determine, is the system an object? An object would be like a block of iron, a chunk of iron. Or is the system a reaction? An object or a reaction? Because we handle these two things totally different. We can confirmed, usually we just confirm that we're dealing with a closed system because most of the time we're dealing with closed systems. And so, are we dealing with a closed system? Sometimes we deal with an isolated system. We pretty much never deal with an open system. But I'd say 99% of the problems you do are going to be closed system. Maybe 1% will be an isolated system in the homework. Just kidding. Okay, then what do we need to know about our system? This is not the same. Remember gas mixtures. Gas mixtures you can define either by Dalton's or Avogadro's. It doesn't make any difference, right? Because it's the same mixture. But here it makes a huge difference in your calculation. For example, you would use a different set of equations because of this. And that is, what? What's the next thing we need to know about our system? Is the system this is very important. Is the system constant volume, or is the system constant pressure? So there are people who do. There are people who use the equations for constant pressure when they're dealing with constant volume, and you go, why are you doing that? Why are you using constant pressure equations when you're dealing with constant volume? It's not going to work. And what makes you think it's going to work? Well, what makes them think it's going to work is because there's no alarm going off. Alarm, warning, warning, you're using the wrong equation. No, you're supposed to have it memorized. That memorization is what kills people, because a lot of people have, including me, have difficulty memorizing things, right? And wait until the night before the test to memorize and fail, Or maybe they have excellent short-term memory. And so what's often done in thermodynamics, like at UCLA, is people repeat it. The second time around, it's a lot easier to memorize that stuff, right? Or the third time around, it gets successively easier. Some people take more time to memorize that stuff. And so you don't have to repeat anything, because if you memorize this stuff now, you're going to be way ahead of most people, when you take thermodynamics. Most majors, you need thermo, like even in biology, you don't think, why do I need thermodynamics in biology? Because, energy, fuel, right, sugar. You need sugar for energy. Your body needs energy. There's a lot of people say, I don't need this math. But you do. They have thermodynamics for biologists, they have thermodynamics for engineers, they have thermodynamics for many majors. And so, the way we handle energy exchange differs for constant volume versus constant pressure. Thermodynamics deals with energy in chemical reactions. And how much energy are we going to get, or how much work can we do, or this or that type of question. And so let's look at some systems here. Let me give you examples of systems. 50.0 grams of iron solid at 325 degrees C. What is that system? Is that system an object, or is that system a reaction? There are only two types of systems, object or reaction. Is that an object or reaction? This is an object. This is a hot object. What do you think this hot object, this hot chunk of iron, is going to do to the surroundings? the surroundings is this lab, or this classroom. What do you think this hot chunk of iron is going to do? Well, it's going to heat up the surroundings, right? We're going to feel it because the air is going to start getting warmer. The table, whatever you set this on, is going to start getting hot. And so this is just a hot object. When we have a hot object, what type of energy, are we looking at? Well, the type of energy we're looking at is, well, hot, heat, temperature is kinetic energy, right? And so this object has high kinetic energy. What about the room? Well, the room is only at 25 degrees C, and the rest of the universe is out. And so, what's going to happen to the room here? It's going to start to gain some of that kinetic energy through transfer, collisions, and the room is going to get warm. So that's a heat process there. Okay, what about this system? This will make the room hot, right? For sure, this is going to make the room hot. But would this make the room hot? Let's say I have 1 mole of methane at 25 degrees C plus 2 moles of oxygen at 25 degrees C. Would that make the room hot? I'll leak out 1 mole. I don't want to leak out 1 mole of methane because that would be like 25 liters of methane in here, right? But I'll leak out a little bit of methane. Is this methane and oxygen going to make the room hot? No, it's not, because if we treat this as an object, well, this object is going to be at the same temperature as the room. But what we have is two situations here. Both of these are hot objects in a way, but this is a hot object in terms of kinetic energy. This is a hot object in terms of potential energy. Because would you want a room full of methane and oxygen? No, because you could cause an explosion. And so, in other words, we think of this having a lot of energy because it's a hot chunk of iron, but we also think of this as having a lot of energy because of the potential for reaction, the potential for explosion. And so this is two different types of energy that we look at. And when we look at the energy, the total energy is what we call the internal energy. The internal energy gets the symbol U in our book, but it also gets other symbols depending on what book you're using. The total energy, or internal energy, is going to equal the, what we call the kinetic energy, which is, kinetic energy is related to what again? Temperature, and potential energy. When we look at the driving force for chemical reactions, we're looking at going from high energy to lower energy, or less stable to more stable. And so in terms of potential energy, where does this is called chemical potential energy. This chemical potential energy, where does it come from? Well, that's going to come from, this. Our system in this case is very different because here we start off with methane and O2. And this is going to have a higher internal energy here than something else. Over here, we start off with a chunk of iron. And so we have iron solid at 325 degrees C. So this is at a higher internal energy. This is a higher internal energy. Eventually this chunk of iron is going to cool down, and so we'll get a chunk of iron solid at 25 degrees C. And so it just cools down back down to room temperature, right? It's not going to stay hot forever. Over here, eventually the methane is going to be oxidized to CO2 and H2O. We get two CO2s in the H2O liquid. And what's going to happen here is, these are all gases. What's going to happen here is eventually it's going to cool back down to 25 degrees C. You know, it's not going to stay, is it going to stay hot forever? No, it's going to cool down at 25 degrees C. Both of these systems are going to lose energy to the surroundings. So energy is going to be exchanged, and in this case, you know, we have a hot chunk of iron cooling down. That's going to release energy to the surroundings. Over here, you know, this is a highly exothermic reaction. This is going to release energy to the surroundings here. Yes. And so this is a critical point here. For example, when we burn methane, is the temperature really at 25 degrees C? You know, so let's go ahead and combust some methane here. That does not look like 25 degrees C, right? This is way hotter than 25 degrees C. Down here, you hit the tip of the cone, that's hot. And so the CO2 in the water coming off here are very hot. Very hot. But the way we deal with this is this. You know, we can figure out, you know, what temperature that's going to be, you know, at its peak, the CO2 in the water. We can do that, but we don't. In thermal, we try to keep things as simple as possible. And so what we do in thermo is we try not to mix what we call kinetic energy with potential energy. We try to keep those separate. And the way we do that is this. Just write this bigger here so I have some more room. The way we do that is like this. So this is iron solid at 325 degrees C, you know, however many grams was. This is iron solid at 325 degrees C. So did anything happen to the chunk of iron? So let's say I had how many grams did I say? 50, oh, okay. So I start off with 50.0 grams of iron. I end up with 50.0 grams of iron. You know, was there any change? Am I going from, you know, weaker or stronger or anything like that? No. So there's no change in potential energy. And we know that the internal energy initial is going to equal the kinetic energy, E sub k, plus the potential energy, which we'll call PE. So this is going to be E sub k initial and the initial potential energy. And then the internal energy final is going to equal E sub k final plus the potential energy final. Now, we look at a chunk of iron, it's still a chunk of iron. Did anything happen to its potential energy? Do we get stronger bonds or weaker bonds or what? No, nothing happened. And so when we look at delta U here, the change in internal energy is equal to the delta E sub k plus delta PE. Delta PE is just PE final minus PE initial. That's 0. And so there was no change in potential energy. So the only change in internal energy here came from the change in kinetic energy. That is, this change in temperature. All objects are like this. objects, when we're dealing with a system that is an object, objects cool or heat up. Cool down or heat up. That's all they can do because nothing happens to their potential energy. They're just an object. They stay the same object. You have a chunk of iron, it stays a chunk of iron, right? And so we're just looking at this exchange or change in kinetic energy. This, kinetic energy is temperature, right? And so there's some kind of change in temperature. And so objects, there's going to be a change in T. Now, this is what we always do for chemical reactions. For chemical reactions, no matter if the temperature skyrockets, is the CO2 and the water vapor that were produced going to stay hot forever? No. And so the methane and the O2 here start off at room temperature, right? And the CO2 and the water vapor that's produced is very hot, but eventually it's going to cool down. Those are hot objects that cool down, and those will again reach room temperature. So in a reaction, we start off with CH4 gas plus O2 gas. This is at 25 degrees C, and then we're going to end up with CO2 gas plus 2H2O. Now, what is H2O at room temperature? A liquid or a gas? I know initially I'm going to form steam, but is that steam going to stay steam? No, eventually it's going to cool down and form liquid water. And so this is going to be at 25 degrees C. So we form H2O liquid. Now, the initial internal energy is going to equal the kinetic energy, which is related to the temperature, 25 degrees C, plus the potential energy, initial. The final internal energy will equal the kinetic energy final plus the potential energy final. And so when we calculate delta U, the change in energy here, internal energy is called the total energy. And so when we look at the change in total energy, we're looking at delta EK, the change in kinetic energy plus the change in potential energy. Here, was there any change in kinetic energy? No, because the temperature initial and the temperature final are the exact same thing. And so all the energy that's being released into the surroundings came from the driving force, right? The change in, we've got stronger bonds here. These are more stable. CO2 and water, right? Think about this as redox. When we think about this as redox, methane's the reducing agent, oxygen's the oxidizer. Over here, what's the oxidizer? Well, CO2 is the oxidizer, water is the reducer. Is CO2 a very good oxidizer? No, CO2 is a really bad oxidizer. What about water? Is water a good reducer? No, water is an awful reducer. These two are very stable, unreactive, right? And so we have that. And so when objects, well, here, reactions, reactions don't cool down or heat up. In a reaction, what we do is we set delta T equal to 0, no matter what, the reaction. Therefore, the change is only in potential energy. We could mix, more advanced. Initially, we just keep it simple, but more advanced problems would be, how much energy is released if the CO2 and water produced were at 1,000, not 1,000, let's say at 300 degrees C, something like that. We can mix and match, but that comes later, once you know how to deal with these, then you, of course you can mix it, potential and kinetic, into problems and make the problems a little bit more difficult. But for right now, we try to keep the problems simple as possible. And so that means you have to be very aware of your of your well, any exchange in internal energy is going to be manifested in terms of how is energy exchanged with the surroundings. The energy is going to be exchanged in terms of heat and work. And so delta U is going to equal Q plus W, the heat and the work. And the same thing over here, delta U is just equal to Q plus W. Well, you know, what happened to all that heat that was generated in this combustion? All that heat must have went out into the surroundings, and the surroundings must have gotten hot because of this chemical reaction here. And so this is why, you know, you combust methane, you cook food, you heat up a pot of water, you do whatever with that, right? And so we'll be looking at heat and work here. Well, let's not get too involved just yet. And so here's some analogy with potential energy in physics. In physics, you have something called gravitational potential energy. You know, this is not a hot object. This is an object at 25 degrees C. You know, this is at high gravitational potential energy. This is at low gravitational potential energy. And so in terms of potential energy, you know, this is like having a brick hanging over your head. You feel uncomfortable because you have this potential explosive mixture, right? And so this is just potential energy, high potential energy, low potential energy. So this is chemical potential energy. Well, chemical potential energy is like this here. You know, you have a tennis ball high off the ground. And then here we can see, you know, that potential energy here, as the potential energy decreases, the kinetic energy increases, so that the total energy is the same. In fact, you guys know the first law of thermodynamics. The first law of thermodynamics is that energy is conserved. In other words, we don't need this analogy. All right. So this is kind of the brief start to this. Now, what we're going to do is we're going to just focus on heat. You know, as the surroundings heat up, what can happen? Well, here, as the iron cools down, what's going to happen to the surroundings? The surroundings is going to warm up. Over here, you know, as this reaction takes place and energy is released, then the surroundings will absorb that energy and heat up, right? Now, how hot will the surroundings get? Well, it depends on how much energy is released here. And so what we can figure out is how much heat is released by this block of iron. And we can figure out how much heat is released in this chemical reaction. And so we're going to be looking at heat next. Q. And so the first thing is we're going to look at heats for objects. Heats for objects are given by something called the heat capacity. And so let's look at that first. So we start off with objects, and we have the heat capacity. There are different types of heat capacity. You know, there's something called the molar heat capacity. There's something called the specific heat. There's something called the heat capacity of an object. The molar heat capacity gives us a ratio. You know, it absorbs this much energy. What happens to the temperature? So for example, if you gave, what are the units for energy? You guys know? Joules. If you gave 1,000 joules of energy to a pot of water versus 1,000 joules of energy to an aluminum plate, are they going to heat up to the same temperature? No, you know, the pot of water is going to take a lot of heat just to warm up because water is such a good heat sink, whereas aluminum just rapidly increases its temperature. Aluminum is not a good heat sink. Aluminum is a poor heat sink. Although it's used as a heat sink because it can dissipate the heat to the air. But anyway, the molar heat capacity just gives us the ratio. Joules of energy is going to cause a mole of this to heat up by degree C. So that's the total. So if I had a mole of whatever object I'm looking at, the heat capacity is going to tell me how many joules are required to warm it up by degree C. The specific heat is different. Rather than a mole, the specific heat just says, if I had a gram, how many joules of heat would I need to heat it up by degree C? The specific heat of an object, excuse me, not the specific heat, the heat capacity of an object is how many joules per object. Sometimes the object's not mentioned per degree C or just joules per degree C, you know, if we're talking about one object. And so, for example, an object would be like a brick. You know, do you want to weigh a brick? Figure out how many grams of bricks you have? Is that even worth it? No. If you have 100 bricks, that's a lot easier. And so, if you know how many joules of energy it requires to heat up a brick by degree C, then you have joules per brick per degree C, right? And then with 100 bricks, we'll just 100 times this. Or sometimes we only deal with one object. For example, a building. You know, if you have the heat capacity, how many buildings are you're going to have one building, right? And so this will be joules per degree C. For example, when we use equipment like a calorimeter. How many calorimeters are we going to be dealing with? One. And so it's always joules per degree C. Technically, it's joules per calorimeter per degree C. But it's, and so with this, you know, we could use a little bit of dimensional analysis to come up with an equation. An equation we use for objects is like this. For objects, again, I'm just going to emphasize that the heat is equal to the amount of object times C. C is the heat capacity object times delta T. And so the units should work out because C is going to be in one of those units. So if we know the amount, then the amounts will cancel out. And we know the temperature change, delta degree C will cancel out, leaving us with joules of heat. And so a lot of people memorize this as Q equals MC delta T in Chem 4, but I'm going to change it a little bit. Rather than using M, because M would imply we must use the specific heat. We don't always have the specific heat. You know, sometimes we have the other heats that we're dealing with. And so using M means you have to weigh everything in grams. No, you don't. Well, determining these is not so difficult. We do some experiments to determine, you know, or take some measurements to determine. So here. When you do that, it turns out, you raise a gram of water by degree C. You know how many joules it takes? 4.18 joules. 4.18 joules is 1 calorie. And so 1 calorie of energy is required to heat up a gram of water by degree C. Let's see some other heat capacities or specific heats in the table here so we can get a comparison. So these are specific heats. So these are going to be per gram. Per gram. Joules per gram per degree C. And so what's the lowest, what's the highest specific heat that you see? See, the lowest is going to be 0.130. So to heat up lead by degree C, does it take much energy? No, a gram of lead only requires 0.13 joules. That's it, to increase the temperature by degree C. So that's not a very good heat sink, you know, the temperature rapidly increases. Whereas water, liquid water, 4.18. 4.18 is that the highest? That's the highest. And so to heat up a liquid water by degree C requires a lot of heat. Does that make sense? Why would it require liquid water so much heat to raise the temperature by degree C, whereas lead, so little heat to raise the temperature by degree C? That's what we want theory to help us answer, huh?
Oh, sorry.
No, go ahead.
Or isn't it that because it's a liquid, so it doesn't have like a fixed structure like solid, so it takes a lot more.
Yeah, the liquids are typically higher. You can see. It's good. Liquids, it has to do with motion. You know, water has lots of different motions. It can rotate, it can vibrate, it can translate. And so there's lots of different motions. There's lots of ways it can absorb energy or become excited. Whereas lead in a crystal, all it can do is vibrate. And so there's not much. So here, a lot of different ways of water can absorb. But the highest would be water. So what does it mean to have a high heat capacity? It means it can absorb a lot of heat. This is a good heat sink. That's why we use water. This is why we have AA, add acids. We use the water as a heat sink. So, you know, we can measure these. You know, you take some measurements and measure the temperature, measure how much energy went in there, etc., and then do the calculation. Or we can use these. When we use these, we're going to apply the first law of thermodynamics. The first law of thermodynamics is this. Let me show you. The first law of thermodynamics is, I'll just end with this, is that Q of the system is equal to minus Q of the surroundings. And then we have to talk about the sign convention next. So we'll start with the sign convention. That's equation 7.7. All right, I'll stop here.